Okay, so today we're going to be looking at motion. Let's have that in a decent colour for a start. That's better. So we're going to have motion in a straight line. Okay, so if we take the x-axis to be the straight line, along which the motion takes place, okay, so we're just going to take the x-axis to be a straight line where we're going to be moving or thinking of things and objects moving. Okay, so we're just talking about horizontally moving. Okay, we're not talking about any vertical movement like gravity involved. Okay, anything like that. The displacement, that's going to be a key word. Okay, the displacement, for anyone that does physics will know what that is defined as the distance from the origin in time t. Okay, and is denoted by, and the notation we use for displacement, again, if you do physics, you'll know what this is. We use the letter S for displacement, and it depends on how many seconds something's moved along. Okay, so S with respect to t. Okay, so that's displacement. It means the distance along from the origin, how many seconds after we've started the motion. Okay, the next thing we want to have a term for is the velocity. Okay, so velocity is defined as the rate of change of displacement with respect to time. Again, that's also time dependent and is denoted v of t. Okay, velocity, we use the symbol v as a function of time t. Okay. Now, if we are saying it is the rate of change of the displacement, what that means is, you remember from higher when you looked at rate of change, it means it's the differential of displacement. So v of t is the differential, should I have it better? Of the displacement function. Okay, you differentiate the displacement function. Or, in other words, v is dx by dt. Okay, you differentiate the displacement. Okay. Now, one last term that we'll need to know is acceleration. And that is defined by the rate of change of velocity with respect to time and is denoted by a of t. Okay, so acceleration, use the letter a for it. Okay, so if we know that is the rate of change with respect to velocity, then again a of t can be written as d by dt of our velocity function vt, okay, v of t, or simply a would be dv by dt, okay. But if velocity is the differential of displacement, and if we differentiate velocity, it means that you're actually doing the second derivative of the displacement function. Okay, so that's the sort of connections between them all. Okay, to get the velocity, you differentiate the displacement. To get the acceleration, you differentiate the velocity, or you differentiate displacement twice. Okay, and that's the sort of rules that we have got there. Okay, so now I want to highlight them there. Okay, so that's the sort of pattern we've got. Again, if you've done physics, you will have seen this before. Okay. So if this has a positive value, it is called, so I'm still talking about the acceleration here, it is called acceleration but if it's negative, then we say deceleration. Okay, so if the acceleration value that we get out is negative, it's actually slowing down, it's negative, okay, it's decelerating as opposed to accelerating. Okay, now we've used notation up there, and that's going to be the notation we use, but we can also use other notations such as, well, if S is displacement, then we can even write that in a shorter hand so that velocity is S dot, you're differentiating displacement there. Okay, and remember S here, S dot would be ds by dt. Okay, therefore, if I differentiate it twice, that would give me the acceleration. So therefore, it would be d squared s by dt squared. Okay, so that's just some other notation that you're free to use, or you might see in some questions. Okay, dot means it's been differentiated once, double dot means it's differentiated twice. Okay, look at a couple of examples, and then we'll look at a way on how we can work back from acceleration back down to displacement later. Okay, so we'll look at a couple of examples of this type of nature first. So start off with example 1. Okay, a car is travelling along a straight road. Okay, the distance S meters. Okay, we're working in meters here. Travelled in t seconds is S equals 10 t minus 5t squared. Okay, so that's our function for the distance, the displacement. Okay. Our question would be find the velocity when t equals 0.5 seconds. Okay. So our job is to find the velocity when t is at 0.5 seconds along the journey. Okay. So, solution. Well, our displacement, our distance formula is 10t minus 5t squared. To get the velocity, that's ds by dt. Therefore, we differentiate this with respect to time, so that's going to give me 10 minus 10t. Okay. And then substitute in the value t equals 0.5, because that's how many seconds I want to find out what the speed would be or the velocity would be at. Therefore, v would be 10, take away 10 lots of 0.5. Therefore, v would give me the answer 5, and it's meters per second. Okay. Now, if you do physics, you may have been able to. You can leave that in terms of advanced higher maths, your units like that. However, in physics, I know you can write your units like that. Okay, meters per second. It means both mean the same way. Okay, it means the same thing. So both are acceptable in the maths. Okay. Are we okay with that example? That's just a quick one to show you that to get the velocity, you just differentiate it, and then we were given a time value to put in to work out what the actual velocity speed was at that time. Are we okay with that? Okay, cool. We'll look at another one, and then we'll look at reversing the process. So, example 2. So, again, a car is travelling along a straight road. The distance s again in meters, travelled in t seconds is s equals 5 plus 2t plus t cubed. Okay, so that's my function there, 5 plus 2t plus t cubed. Our job will be to find two things, so find the velocity and acceleration at time t equals 3 seconds. Okay, so that's our question. We've got two things to work out. We want to try and find the velocity and the acceleration here for this car travelling on a straight road. So, again, first it will be almost identical to the last one. So, start off with our function, which is 5 plus 2t plus t cubed. Well, we want the velocity, so that's ds by dt. Therefore, that would give me 2 plus 3t squared. Then at time t equals 3, okay, and the velocity would be 2 plus 3 lots of, 3 squared, which would give me 29 meters per second. Okay, so that's how fast that car is going, 29 meters per second. If I want to work out the acceleration, well, the acceleration is the velocity function differentiated. Okay, so it's dv by dt. Then my velocity function was this over here. So if I differentiate that, I'm going to just get 6t. Therefore, at t equals 3, a would equal 6 lots of 3, which would equal 18. Now, again, it depends on how you write this down, so I just want to show you both ways. Then That's how you'd write it for acceleration, meters per second squared. Okay, because you've done it twice, okay? Or it would be 18 meters per second squared like that, s to the minus 2. Okay, so that's just notation for the units. But are we okay with that example there? So that was asking us to find both. We just had to differentiate the function twice. Once for velocity, twice for acceleration, subdividing. Are we okay with that? Okay, cool. Right, but we can also reverse the process. Okay, so we can reverse the process. So therefore, if I wanted to work out my displacement, then I would integrate the velocity function. Okay, because to get the velocity, we differentiate displacement, so we do the opposite. We would integrate the velocity function. And likewise, if I wanted to work out the velocity function, I could either differentiate the displacement if I had that, or if I know the acceleration, I would integrate the acceleration function. Okay, so it's just the opposite way. Okay, so in other words, you're just working back. Okay, so how you would originally get to it, you do the opposite to get back to what it was before. Okay, and we'll look at this one example to highlight both these. There'll be two parts to it though. So, example 3. A particle moves in a straight line such that its acceleration which will be a meters per second squared after t seconds is given by a equals 4t. Okay, so that's my function for acceleration, a equals 4t. Initially, the velocity of the particle is positive 3 meters per second. Okay, so the initial velocity of this particle at the very start of this process, it's going at 3 meters per second in the right direction, the positive direction. So our job is to find two things. So find in part A the acceleration of the particle after 5 seconds. That's the first thing we want to do. And part B, the velocity of the particle after 2 seconds. Okay, so those are the two things that we want to try and work out and evaluate. We want to work out the acceleration of the particle after 5 seconds, the velocity after 2 seconds, and the only thing we know is we know our acceleration function is a equals 4t, and initially we know that the velocity was moving in the right direction, the positive direction at 3 meters per second. Okay, so let's see how we do this. So part A, okay, so it's a solution. Well, to work out acceleration at 5 seconds, I'm just going to substitute that into my formula, or my function, sorry, for acceleration. So a equals 4t, okay, that's what my function was. So at t equals 5 seconds, a would equal 4 lots of 5. 4 lots of 5 would be 20. And again, our units would be 20 metres per second squared. Okay, so there wasn't actually anything really for us to do apart from substitute that in. Okay, so that was quite a nice one to start off with. So, part B, okay, let's try and solve and find the velocity after 2 seconds. Well, I know the velocity is the acceleration function integrated. Okay, so I need to integrate the acceleration function, which means I'm integrating the value of the function for t, respect to time, which would be 2t squared plus c. Okay, so remember you've got your constant. Okay, you need to attach your constant there. Now, if we wanted to substitute in the value for 2 seconds, you're going to see I'm not going to get an answer straight out yet, am I? Because I'm going to have this constant that I still need to work out with. That's where the initial data came in. So we did know that initially the velocity of the particle was at plus 3 metres per second, which means here that at time equals 0, I know the velocity was 3. Okay, because initially means at the very, very start. Okay, so that means that if I just take this up to like v equals 2t squared plus c here, so you can actually see what I'm actually doing here a bit more better, then that means if I substitute these into here, then 3 would equal 2 lots of 0 squared plus c. Therefore, the constant would be the value 3. Okay, that's what that would be, because this bit here just vanishes, goes to 0, we're left with plus c. Okay, therefore my function, velocity of t, is actually 2t squared plus 3. Okay, so that's not me finding the final answer yet, that's me just found out what the constant is. Now I can work out what I was asked to do, so at t equals, is it 2 seconds I think it was? Yep, 2 seconds. Then if I substitute 2 into this, it's going to be 2 multiplied by 2 squared plus 3. And if you work that out, that'll give you 11 metres per second. Okay, are we okay with that example there when we had to work back? Yeah. Okay,